Hello everyone, I'm Eric Lima and today I'm going to present our work modeling of the parabolic kick device of omnidirectional robots that I developed with Daniela Vaccarini, Reinaldo Lima, Professor Marcos Massimo and Professor Luis Carlos Góes. Here's a brief introduction. I'm part of ETA Androids, the robotics team at ETA, and I'm part of the Small Size League, which is one of the categories of RoboCup. In this category, we focus on the problem of multi-agent cooperation and control in highly dynamic environments. Over the years, some mechanisms that help multi-agent cooperation have emerged. Some of these mechanisms are the kicker, dribbler, and the chipper. In this work, the chipper was developed, which is the mechanism responsible for performing high kicks, enabling plays with passes and kicks for coverage. In the image on the side, we have a small size league robot and an example of a chipper mechanism with a solenoid actuator. Well, with all that in mind, the objective of this research was the mathematical modeling and the development of a cheaper design considering the electromechanical effects. Furthermore, the objective was to perform the optimization of the mechanical parameters of the chipper using well-established computational optimization techniques. Some works, such as the one mentioned, developed the electromechanical model in a similar way to the one developed in this work. Small size league team works, such as the one developed by Immortals, present similar ideas to this work to perform the chipper optimization. However, to the best of our knowledge, no work has used computational optimization algorithms in order to find the best chipper geometry, something that was possible to develop in this work. Well, the mechanism adopted in this work was the electromechanical mechanism. In this mechanism, there is a RLC circuit with a capacitor in parallel with the voltage source. When the switch is changed from 1 to 2, this capacitor will be discharged through the inductor, which in this case will be a solenoid. Here in figure B we have a section of this solenoid, and inside the solenoid there is a plunger of ferromagnetic material, which will be accelerated due to the magnetic field generated by the solenoid. The objective of this stage of the project is to discover the speed that this plunger has as function of time. In this sense, through the manipulation of mathematical equations, it is possible to arrive at this equation of the magnetic circuit, in which the inductance of solenoid as a function of displacement x is given by this expression, where μ0 is the permittivity of the environment, n is the number of wire turns around the solenoid, a is the section area, x is the displacement of the plunger with respect to the solenoid, μr is the related permittivity of the plunger with respect to the environment, and d is the length of our solenoid. In addition, we have a spring, which serves to return the plunger to its original position after the kick has been made, and a shock absorber, which serves to prevent sudden movements of the plunger. Well, from Newton's second law, we can arrive at this second expression, where V is the velocity of the plunger that we want to obtain, I is the electric current passing through the solenoid, M is the mass of the plunger, K is the spring constant, and B is the damping constant of the shock absorber. Well, here in figure 3 we have a side view of our system, where here in blue we have our plunger, in gray we have our chipper, and in orange we have the ball. When the plunger exits the solenoid, it will collide with the chipper, propelling the chipper plus ball set. In this sense, from the principles of momentum conservation and energy conservation, we can arrive at this first equation, where omega is the angular velocity of the chipper plus ball set, v1 is the velocity of the plunger before the collision, dy is the vertical distance from the axis O to the plunger, I is the moment of inertia of the chipper plus ball set, and m is the mass of the plunger. After the chipper plus ball set obtains an omega counterclockwise angular velocity, it will be torqued by the weight force in the opposite direction of its movement. Such torque can be calculated from the second law, where m is the mass of the chipper plus ball set, g is gravity, r is the distance from axis O to the center of mass of the set, theta is the angular displacement of the set with respect to the vertical, I is the moment of inertia of the set, and alpha is the angular deceleration that our set is undergoing. This set will perform this rotational movement until the chipper collides with the brake. Such a brake can be better visualized on this slide, and it is represented by these two black threads. where the chipper will collide and stop its counterclockwise rotational movement. However, such a break will not stop the ball. So the ball will continue its movement with the same speed as it had just before the collision, and it will start a parabolic movement. Thus, with all these equations shown, it is possible to simulate such a system in a Simulink environment, thus being able to obtain the distance traveled by the ball and its maximum height reached. Well, now with our mechanism fully defined, we can optimize the chipper. The chipper can be defined through 4 dimensions: the thickness E, the first height h, the overall height p of the chipper, and the slope theta of the chipper's leg. The objective is to find the values of these 4 dimensions that optimize the mechanism. As the optimization deals with 4 parameters, the CMAES algorithm was implemented, since this algorithm performs well with a high number of parameters. In addition, a simple evolutionary strategy, SES, was implemented, and both implementations were compared. Since we want to maximize the exit velocity of the ball as it detaches from the chipper, we need to maximize the omega, which is the angular velocity of the set. So we have to minimize the objective function gamma, which is equal to the moment of inertia of our set divided by the distance from the O-axis to the base of the chipper. In this sense, it is necessary to find the moment of inertia according to the 4 parameters defined in the previous slide. The approach to perform this calculation was to divide the set into 5 parts to facilitate the analysis of the moment of inertia of the set in relation to the O-axis. Furthermore, CMAES does not deal directly with constraints. That is, it does not prevent the algorithm from finding absurd solutions, such as negative dimensions or dimensions that tend to 0. Thus, a strategy of adding constraints through an addition of high cost in the objective function was adopted, so that the algorithm does not find unwanted solutions. Well, after simulating the system in Simulink, it was possible to determine the speed of the plunger as a function of the time that the capacitor is kept discharging in the circuit. Furthermore, in figure B, we have the speed of the chipper plus ball set during its rotational movement, in which it is under the action of the torque of the weight force. In this graph, it is noted that the action of torque in this movement is negligible, since the speed of the set remains practically constant throughout its movement. So, to simplify the simulation, this deceleration of the torque was neglected. Thus, it is now possible to associate the angular velocity of the set with the total distance covered and the maximum height reached by the ball. In these 2 figures, we can observe the total distance covered and the maximum height reached by the ball as a function of the time the capacitor is kept discharging the circuit. In this sense, if we want the ball to reach a smaller distance or height, we just have to regulate the time in which we keep the capacitor discharging in the circuit. After the optimization of the chipper, the graph of the performance of the algorithms was obtained, and it is noted that both algorithms were able to converge to local optimums. But CMAES was able to achieve a better local optimum than the SES algorithm. Furthermore, in figure A, it is possible to observe the technical design of the chipper obtained using the parameters generated after the optimization. Finally, it is possible to compare the performance of the old chipper with the optimized chipper in relation to the distance and maximum height reached by the ball. It can be seen from this data that the optimized chipper achieved an increase of about 40% compared to the old chipper, demonstrating a significant improvement in the performance of the parts. Therefore, through this work, it was possible to assemble a simulation capable of satisfactorily representing the proposed system. It was possible to build a direct relationship between the parameters of the oblique throwing of the ball with the time interval which the capacitor is kept discharging the circuit, which opens several possibilities of strategy for our team. Also, it was possible to develop an optimization capable of significantly improving the performance of the piece. Finally, perspectives for future works are the making and assembling of the chipper and conducting experimental tests to validate the theoretical model, something that was not possible due to the COVID-19 pandemic. Finally, I thank CNPq for the scientific initiation scholarship offered, something that was of great help for the progress of the project. Also, we would like to thank to all EatAndroid sponsors. And thank you for your attention.